So I'm going to be doing just recording Wikipedia articles. I'm going to read them out loud. I'm going to read the Planck Constant. Well, let's see. Yeah, let's read the Planck Constant out loud. The Planck Constant. The Planck Constant, or Planck's Constant, is a fundamental constant denoted by h, and is of fundamental importance in quantum mechanics. Let me just X out quantum mechanics and mathematical foundation of quantum mechanics. And I've recorded the Wikipedia article for quantum mechanics out loud. And is of fundamental importance in quantum mechanics. A photon's energy is equal to its frequency multiplied by the Planck constant. Due to the mass-energy equivalence, the Planck constant also relates mass to frequency. And this is actually how mass is defined. Here in metrology, it is used together with other constants to define the kilogram and SI unit. The SI units are defined in such a way that when the Planck constant is expressed in SI units as the exact value h equals 6.6260715 times 10 to the minus 34th joules inverse Hertz. Now, is that co-data? And they should have... Okay, whatever. At the end of the 19th century... maybe this is the 9th edition of the brochure. Okay, well, anyways. At the end of the 19th century, accurate measurements of the spectrum of blackbody radiation existed, but the distribution of those measurements at higher frequencies diverged significantly and was predicted by then existing theories. In 1900, Max Planck empirically derived a formula for the observed spectrum. He assumed a hypothetical electrically charged oscillator in a cavity that contained blackbody radiation could only change its energy in a minimal increment e that was proportional to the frequency of its associated electromagnetic wave. Where was I? Max Planck. Okay, in 1900, Max Planck empirically derived a formula for the observed spectrum. He assumed a hypothetical electrically charged oscillator in a cavity that contained blackbody radiation could only change its energy in a minimal increment e that was proportional to the frequency of its associated electromagnetic wave. Let me scooch up. And we have Planck constant. Common symbols h or h bar for the reduced Planck constant. Dimension: mass times length squared times inverse time. He was able to calculate the proportionality constant from the experimental measurements, and that constant is named in his honor. In 1905, Albert Einstein determined a quantum of minimal element of the energy of the electromagnetic wave itself. The light quantum behaved in some respects as an electrically neutral particle and was eventually called a photon. Max Planck received the 1918 Nobel Prize in Physics in recognition of the services he rendered to the advancement of physics by his discovery of energy quanta. We have some values here. Anyways. Origin of the constant. Main article. Planck's law. Planck's constant was formulated as part of Max Planck's successful effort to produce a mathematical expression that accurately predicted the observed spectral distribution of thermal radiation from a closed furnace, blackbody radiation. This mathematical expression is now known as Planck's law. In the last years of the 19th century, Max Planck was investigating the problem of blackbody radiation first posed by Kirchhoff some 40 years earlier. Every physical body spontaneously and continuously emits electromagnetic radiation. There was no expression or explanation for the overall shape of the observed emission spectrum. At the time, Wien's law fit the data for short wavelengths and high temperatures, but failed for long wavelengths. Also around this time, but unknown to Planck, Gord Rayleigh had derived theoretically a formula now known as the Rayleigh-Jeans law that could reasonably project long wavelengths, but failed dramatically at short wavelengths. According to this problem, Planck hypothesized that the equations of motion for light describe a set of harmonic oscillators, one for each possible frequency. He examined how the entropy of the oscillators varied with the temperature of the body, trying to match Wien's law, and was able to derive an approximate mathematical function for the blackbody spectrum, which gave a simple empirical formula for long wavelengths. Planck tried to find a mathematical expression that could reproduce Wien's law for short wavelengths and the empirical formula for long wavelengths. This expression included a constant h, which is thought to be for a Hills-Graph auxiliary variable, and it subsequently became known as the Planck constant. The expression formulated by Planck showed that the spectral radiance of a body for frequency v at absolute temperature T is given by v sub v of v and T is 2hv cubed over c squared times 1 over e to the power of hv divided by k sub bt minus 1, where k sub b is the Boltzmann constant, h is the Planck constant, and c is the speed of light in the vacuum, whether material or vacuum. The spectral radiance of a body b sub v describes the amount of energy it emits at different radiation frequencies. It is the power emitted per unit area of the body per unit solid angle of emission per unit frequency. The spectral radiance can also be expressed per unit wavelength lambda instead of per unit frequency. In this case, it is given by b sub lambda of lambda and t equals 2h times c squared divided by lambda to the 5th power times 1 over e to the power of hc over lambda times k sub b times t minus 1, showing how radiated energy emitted at shorter wavelengths increases more rapidly with temperature than energy emitted at longer wavelengths. Planck's law may also be expressed in other terms, such as the number of photons emitted at a certain wavelength, or the energy density in a volume of radiation. The SI units of B sub v are watts, inverse steradians, inverse meters, inverse hertz, while those of B sub lambda are watts, inverse steradians, inverse cubic meters. Planck soon realized that his solution was not unique. There were several different solutions, each of which gave a different value for the entropy of the oscillators. To save his theory, Planck resorted to the then controversial theory of statistical mechanics, which he described as an act of despair. I was ready to sacrifice any of my previous convictions about physics. One of his new conditions was to interpret U sub n, the vibrational energy of n oscillators, not as a continuous, infinitely divisible quantity, but as a discrete quantity composed of an integral number of finite equal parts. Let us call each such part the energy element E, Planck, on the law of distribution of energy in the normal spectrum. With this new condition, Planck had imposed the quantization of the energy of the oscillators, a purely formal assumption. Actually, I did not think much about it in his own words, but the one that would revolutionize physics. Applying this new approach to Wien's displacement law showed that the energy element must be proportional to the frequency of the oscillator, the first version of what is now sometimes termed the Planck-Einstein relation E equals hf. Planck was able to calculate the value of h from experimental data on blackbody radiation. His result, 6.55 times 10 to the minus 34 inverse joules, is within 1.2% of the currently accepted value. He also made the first determination of the Boltzmann constant K sub b from the same data and theory. And we have some pictures here. We have Max Planck at the Humboldt University of Berlin. Max Planck, who discovered the elementary quantum of action H, taught here from 1889 to 1928. And intensity of light emitted from a blackbody. Each curve represents behavior at different body temperatures. Planck's constant H is used to explain the shape of these curves. So you have 5,550 Kelvin. This is the wavelength divided by nanometers. This is the spectral energy density divided by kilojoules divided by cubic meters times nanometers. Oh my gosh, I'm going to bit my mosquitoes. Development and application. The blackbody problem was revisited in 1905 when Lord Rayleigh and James Jeans on the one hand, Albert Einstein on the one hand, independently proved that classical electromagnetism could never account for the observed spectra. These proofs are commonly known as the ultraviolet catastrophe, a name coined by Paul Ehrenfest in 1911. They contributed greatly, along with Einstein's work on the photoelectric effect, in convincing physicists that Planck's postulate of quantized energy levels was more than a mere mathematical formalism. The first Solvay conference in 1911 was devoted to the theory of radiation and quanta. Photoelectric effect. Main article, photoelectric effect. The photoelectric effect is the emission of electrons, called photoelectrons, from a surface when light is shown on it. It was first observed by Alexander Edmund Becquerel in 1839. The credit is usually reserved for Henrik Hertz, who published the first thorough investigation in 1887. Another particularly thorough investigation was published by Philip Lenard in 1902. Einstein's 1905 paper discussing the effect in terms of light quanta would earn him the Nobel Prize in 1921, after his predictions had been confirmed by the experimental work of Robert Andrews Millikan. The Nobel Committee awarded the prize for his work on the photoelectric effect rather than relativity, both because of a bias against purely theoretical physics not grounded in discovery or experiment, and dissent amongst its members as to the actual proof that relativity was real. Before Einstein's paper, electromagnetic radiation such as visible light was considered to behave as a wave, hence the use of the terms frequency and wavelength to characterize different types of radiation. The energy transferred by a wave in a given time is called its intensity. The light from a theater spotlight is more intense than light from a domestic light bulb. That is to say that the spotlight gives out more energy per unit time than per unit space, and hence consumes more electricity than the ordinary bulb, although the color of the light might be very similar. Other waves, such as sound or the waves crashing against the seafront, also have their intensity. However, the energy account of the photoelectric effect didn't seem to agree with the wave description of light. The photoelectrons emitted as a result of the photoelectric effect have a certain kinetic energy which can be measured. This kinetic energy for each photoelectron is independent of the intensity of the light, but depends linearly on the frequency. And if its frequency is too low, corresponding to a photon energy that is less than the work function of the material, no photoelectrons are emitted at all unless a plurality of photons whose energetic sum is greater than the energy of the photoelectrons act virtually simultaneously multiphoton effect. Assuming the frequency is high enough to cause the photoelectric effect, a rise in intensity of the light source causes more photoelectrons to be emitted with the same kinetic energy rather than the same number of photoelectrons to be emitted with higher kinetic energy. Einstein's explanation for these observations was that light itself is quantized, that the energy of light is not transferred continuously as in a classical wave, but only in small packets or quanta. The size of these packets of energy, which would later be named photons, was to be the same as Planck's energy element, giving the modern version of the Planck-Einstein relation E equals hf. Einstein's postulate was later proved experimentally. The constant proportionality between the frequency of incident light, F, and the kinetic energy of for electrons, E, was shown to be equal to the Planck constant, H. Atomic structure. And it was John William Nicholson in 1912 who introduced H-bar into the theory of the atom, which was the first quantum and nuclear atom and the first revolution and the first quantized angular momentum as H divided by 2 pi. Niels Bohr quoted him in his 1913 paper of the Bohr model of the atom. The influence of the work of Nicholson's nuclear quantum atomic model and Bohr's model has been written about by many historians. Niels Bohr introduced the third quantized model of the atom in 1913 in an attempt to overcome a major shortcoming of Rutherford's classical model. The first quantized model of the atom, introduced in 1910 by Arthur Eirich Haas and much discussed at the 1911 Solvay conference. Okay, that's a grammatical error. We're going to edit this Wikipedia article. I have a Wikipedia account. The first quantized model of the atom was introduced in 1910 and was discussed at the 1911. That makes more sense. 11 Solvay conference. In classical electrodynamics, a charge moving in a circle should radiate electromagnetic radiation. If that charge were to be an electron orbiting a nucleus, the radiation would cause it to lose energy and spiral down to the nucleus. Bohr solved this problem with explicit reference to Planck's work. An electron in a Bohr atomic could only have certain defined energies, E sub m. E sub n equals negative hc r sub infinity n squared, where c is the speed of light in vacuum, r sub infinity is an experimentally determined constant. The Rydberg constant n is 1, 2, 3. Once the electron reaches the lowest energy level, n equals 1, it cannot get any closer to the nucleus, lower energy. This approach also allowed Bohr to account for the Rydberg formula, an empirical description of the atomic spectrum of hydrogen, and to account for the value of the Rydberg constant r in terms of other fundamental constants. Bohr also introduced the quantity h bar equals h divided by 2 pi, now known as the reduced Planck constant, as the quantum of angular momentum. At first, Bohr thought that this was the angular momentum of each electron in an atom. This proved incorrect, and despite developments by Sommerfeld and others, an accurate description of the electron angular momentum proved beyond the Bohr model. The correct quantization rules for electrons, which the energy... I want to add a hyperlink to Sommerfeld, because I don't know who Sommerfeld is. Come on, get in here. Sommerfeld. That link, done. Hyperlink. Inserted. Who's Sommerfeld? Oh, come on, who messed with the internet? Darn it. Alright, well, now there's an accurate description of the is it working now? And others, an accurate description of the electron angular momentum proved beyond the Bohr model. The correct quantization rules for electrons in which the energy reduces to the Bohr model equation in the case of the hydrogen atom were given by Heisenberg's matrix mechanics in 1925 and the Schrödinger wave equation in 1926. I think I clicked a note. The reduced Planck constant remains a fundamental quantum of angular momenta. Okay, here we go. Arnold Schwarzenegger was a German theoretical physicist who pioneered developments in atomic and quantum physics and also educated and mentored many students for the new era of theoretical physics. He served as a doctoral supervisor for many Nobel Prize winners in physics and chemistry. Only J.J. Thomson's record of mentorship is comparable to his. He introduced the second quantum number, azimuthal quantum number, and the third quantum number, magnetic quantum number. He also introduced the fine structure constant and pioneered X-ray wave theory. Man, he has a bunch of stuff named after him. What's that? Okay, the reduced Planck constant remains the fundamental quantum of angular momentum. In modern terms, if J is the total angular momentum of a system with rotational invariance, and J sub z the angular momentum measured along any given direction, these quantities can only take on the values J squared equals J times J plus 1. Wait, what is lowercase j? J times J plus 1, h bar squared, J equals 0, 1 half, 1, 3 halves. Oh, okay. J sub z equals m, h bar, m equals negative j plus 1 to j. Uncertainty principle. The Planck constant also occurs in statements of Werner-Heisenberg's uncertainty principle. Given numerous particles prepared in the same state, the uncertainty in their position delta x and the uncertainty in their momentum, delta x sub p, obey delta x, delta p is greater than or equal to h bar over 2, where the uncertainty is given as the standard deviation of the measured value from its expected value. There are several other such pairs of physically measured conjugate variables which obey a similar rule. One is time versus energy. Okay, let me just check out conjugate variables. Conjugate variables. Conjugate variables are pairs of variables mathematically defined in such a way that they become Fourier transform duals, more generally related through Pontryagin duality. The duality relations lead naturally to an uncertainty relation in physics called the Heisenberg uncertainty principle between them. In mathematical terms, conjugate variables are part of a symplectic basis, and the uncertainty relation corresponds to the symplectic form. Also, conjugate variables are related by Noether's theorem, which states that if the laws of physics are invariant with respect to a change of one of the conjugate variables, then their conjugate variable will not change with time, i.e. will be conserved. Examples. There are many types of conjugate variables depending on the type of work a certain system is doing or is being subjected to. Examples of canonically conjugate variables include the following. Time and frequency. The longer a musical note is sustained, the more precisely we know its frequency, but it spans a longer duration, and thus a more distributed event or instant in time. Conversely, a very short musical note becomes just a click, and so is more temporally localized, but we can't determine its frequency very accurately. Doppler and range. The more we know about how far away a target is, the less we know about the exact velocity of approach or retreat, and vice versa. In this case, the two-dimensional function of Doppler and range is known as a radar ambiguity function or radar ambiguity diagram. Oh, that's cool. So, like, okay, whatever. Surface energy. Surface tension, wait, what? That doesn't really make any sense. Elastic stretching. Derivatives of action. In classic physics, the derivatives of action are conjugate variables of the quantity with respect to which one is differentiating. In quantum mechanics, these same pairs of variables are related by the Heisenberg uncertainty principle. The energy of a particle at a certain event is the negative of the derivative of the action along a trajectory of that particle ending at that event with respect to the time of the event. The linear momentum of a particle... let me just... In post-radar and sonar sound processing, an ambiguity function is a two-dimensional function of propagation delay, tau, and a Doppler frequency, f. It represents the distortion of the return pulse due to a received matched filter, commonly but not exclusively used in post-compression radar, of the return from a moving target. The ambiguity function is defined by the properties of the pulse and the filter, not any particular target scenario. Many definitions of the ambiguity function exist. Some are restricted to narrowband signals, and others are suitable to describe the delay and Doppler relationship of wideband signals. Often the definition of the ambiguity function is given as the magnitude squared of other definitions. Wise. For a complex baseband pulse S of t, the narrowband ambiguity function is given by this, where it denotes the complex conjugate and I the imaginary unit. Note that for the zero Doppler shift, this corresponds to an autocorrelation of S of t. A more concise way of representing the ambiguity function consists of examining the one-dimensional zero delay and zero Doppler cuts. The matched filter output is an output of time. The signal one would observe in a radar system is a Doppler cut. Oh, here's some cool pictures. That's cool. Then classical derivatives of action. In classical physics, the derivatives of action are conjugate variables to the quantity with respect to which one is differentiating. In quantum mechanics, these same pairs of variables are related by the Heisenberg uncertainty principle. The energy of a particle at a certain event is the negative of the derivative of the action along a trajectory of that particle ending at that event with respect to the time of the event. The linear momentum of a particle is the derivative of its action with respect to its position. The angular momentum of a particle is the derivative of its action with respect to its orientation, angular position. Okay, what is orientation? Geometry. Changing orientation of a rigid body is the same as rotating the axes of a reference frame attached to it. That's cool. The angular the mass moment of a particle is the negative of the derivative of its action with respect to its rapidity. What is rapidity? Rapidity. In relativity, rapidity is commonly used as a measure for relativistic velocity. Mathematically, rapidity can be defined as the hyperbolic angle that differentiates two frames of reference in relative motion, each frame being associated with distance and time coordinates. For one-dimensional motion, rapidities are additive, whereas velocities must be combined with Einstein's velocity addition formula. For low speeds, rapidity and velocity are proportional, but for higher velocities, rapidity takes a larger value, with the rapidity of light being infinite. Oh, that's cool. The electric potential at an event is the negative of the derivative of the action of the electromagnetic field with respect to the density of free electric charge at the event. The electric field in an event is the derivative of the action of the electromagnetic field with respect to the electric polarization density at the event. The magnetic induction in an event is the derivative of the action of the electromagnetic field with respect to the magnetization of that event. The Newtonian gravitational potential in an event is the negative of the derivative of the Newtonian gravitational with respect to the mass density at that event. Quantum theory. In quantum mechanics, conjugate variables are realized as pairs of observables. Okay, well, I don't really want to read all that, but yeah, I got kind of distracted there, but you know, it's fun to follow hyperlinks. There are several other pairs of physically measurable conjugate variables which obey a similar rule. One example is time versus energy. The inverse relationship between the uncertainty of the two conjugate variables forces a trade-off in quantum experiments, as measuring one quantity more precisely results in the other quantity becoming imprecise. In addition to some assumptions underlying the interpretation of certain values in the quantum mechanical formulation, one of the fundamental cornerstones to the entire theory lies in the commutator relationship between the position operator x hat and the momentum operator p hat. X hat, p hat commutate to negative I, h bar, Kronecker delta, where this symbol is the Kronecker delta. Photon energy. The Planck relation connects the particular photon energy E with its associated wave frequency f. E equals hf. This energy is extremely small in terms of ordinarily perceived everyday objects. Since the frequency f, wavelength lambda, and speed of light c are related by f equals c divided by lambda, this relation can also be expressed as E equals hc divided by lambda. De Broglie wavelength. In 1923, Louis de Broglie generalized the Planck-Einstein relation by postulating that the Planck constant represents the proportionality between the momentum and quantum wavelength of not just the photon, but the quantum wavelength of any particle. This was confirmed by experiments soon after. This holds throughout the quantum theory, including electrodynamics. The de Broglie wavelength lambda of the particle is given by lambda equals h over p, where p denotes the linear momentum of a particle such as a photon or any other elementary particle. The energy of a photon with angular frequency omega equals 2 pi f is given by E equals h bar omega, while its linear momentum relates to p equals h bar k, where k is an angular wave number. These two relations are the temporal and spatial parts of a special relativistic expression involving 4 vectors. Okay, what is a 4 vector? Come on, click. A 4 vector is... it's a Minkowski spacetime. Well, we'll get to that later. Statistical mechanics. Classical statistical mechanics requires the existence of h, but does not define its value. Eventually, following upon Planck's discovery, it was speculated that the physical action could not take on arbitrary value, but instead was restricted to integer multiples of a very small quantity, the elementary quantum of action called the Planck Constant. This was a significant conceptual part of the so-called old quantum theory developed by physicists including Bohr, Sommerfeld, and Ishara. Okay, I've never heard of this guy. Who's Ishara? Jun was a Japanese theoretical physicist known for his works on the electronic theory of metals, the theory of relativity, and quantum theory. Being the only Japanese scientist who made an original contribution to the old quantum theory, in 1915, independently of other scientists, he formulated quantization rules for systems with several degrees of freedom. Okay. This was part of this was a significant part of the so-called old quantum theory developed by physicists including Bohr, Sommerfeld, and Ishara, in which particle trajectories exist but are hidden, but quantum laws constrain them based on their action. This view has been replaced by fully modern quantum theory, in which definite trajectories of motion do not even exist. Rather, the particle is represented by a wave function spread out in space and in time. Thus, there is no value. The action is classically defined. Related to this is the concept of energy quantization, which existed in old quantum theory and also exists in altered form in modern quantum physics. Classical physics cannot explain either quantization of energy or lack of classical particle motion. In many cases, such as for monochromatic light or for atoms, the quantization of energy also implies... okay, wait, I have to pause this real quick. Okay, I just had to pause real quick. This view has been fully replaced by fully modern quantum theory, in which definite trajectories of motion do not even exist. Rather, the particle is represented by a wave function spread out in space and time. Thus, there is no value. The action is classically defined. Related to this is the concept of energy quantization, which exists in the old quantum theory and also existed in an altered form of modern quantum physics. Classical physics cannot explain either quantization of energy or the lack of classical particle motion. in many cases, such as for monochromatic light from atoms, quantization of energy also implies that only certain energy levels are allowed and values in between are forbidden. Reduced Planck constant. Implicit in the dimensions of the Planck constant is the fact that the SI unit frequency, the Hertz, represents one complete cycle, 360 degrees, or 2 pi radians per second. In applications where it is natural to use the angular frequency, i.e. where the frequency is expressed in terms of radians per second instead of cycles per second or Hertz, it is often used to absorb a factor of 2 pi into the Planck constant. The resulting constant is called the reduced Planck constant. It is equal to the Planck constant divided by 2 pi and is denoted by h bar, pronounced h bar equals h divided by 2 pi. Value. The Planck constant has dimensions of angular momentum. In SI units, the Planck constant is expressed in joules per hertz, joules inverse hertz, or joules per second, or joules second. Here, let me make an edit here. Come on. Or joules. I'm going to add some math here. Here, let me just copy that. Joules seconds for Planck constant dimensions. In SI units, the Planck constant is expressed. Okay, h equals 6.6. H equals 6.62607015 times 10 to the minus 34 joules inverse hertz. H bar equals h divided by 2 pi equals 1.054571817 times 10 to the minus 34 joules seconds equals 6.582119 times 10 to the minus 16th electron volt seconds. The above values have been adopted as fixed in the 2019 redefinition of the SI base units. Natural units. In the system of natural units used by theoretical physicists, h bar, the reduced Planck constant, is defined to be exactly 1. In these units, h is then exactly 2 pi. Understanding the fixing of the value of h. Since 2019, the numerical value of the Planck constant has been fixed with a finite decimal representation. Under the present definition of the kilogram, it states that the kilogram is defined by taking the fixed numerical value of h to be 6.62607015 times 10 to the minus negative 34 and expressed in the unit joule seconds, which is equal to kilogram meters squared inverse seconds, where the meter and the second are defined in terms of the speed of light c and the duration of the hyperfine transition of the ground state of an unperturbed cesium-133 atom. This implies that mass metrology is now aimed at finding the value of 1 kilogram, and thus it is kilogram, which is, and thus, wait, this is, that makes sense. This implies that mass metrology, aims to find the value of 1 kilogram, and the kilogram is compensating. Okay, I don't really get what they're saying here, but reword a sentence for clarification. Every experiment aiming to measure the kilogram, such as the Kibble balance and X-ray crystal density method, will essentially find the value of a kilogram. As an illustration of this, suppose the decision of making h to be exact was taken in 2010, when its measured value was 6.62606957 times 10 to the minus 34 joules seconds. Thus, the present definition of a kilogram was also enforced. In the future, the value of 1 kilogram must be refined to the current value divided by the past value is about 1.00000001 times the mass of the international prototype of the kilogram, IPK. Significance of the value. The Planck constant is related to the quantization of light and matter. It can be seen as a subatomic scale constant. In a unit system adopted to subatomic scales, the electron volt is the appropriate unit of energy, and the petahertz the appropriate unit of frequency. Okay, what is the petahertz? The petahertz, okay, where was it? The petahertz, atomic unit systems are based in part on the Planck constant. The physical meaning of the Planck constant could suggest some basic features of our physical world. The Planck constant is one of the smallest constants used in physics. This reflects the fact that on a scale adapted to humans, where energies are typical of the order of kilojoules and times are typical of the order of seconds or minutes, the Planck constant is very small. One can regard the Planck constant to be only relevant to the microscopic scale instead of the microscopic scale in our everyday experience. Equivalently, the order of the Planck constant reflects the fact that everyday objects and systems are made up of a large number of microscopic particles. For example, green light with a wavelength of 555 nanometers, a wavelength that can be perceived by the human eye to be green, has a frequency of 540 terahertz, 540 times 10 to the 12th hertz. Each photon has an energy E equals HF equals 358 times 10 to the minus 19 joules. That is a very small amount of energy in terms of everyday experience, but everyday experience is not concerned with individual photons any more than with individual atoms or molecules. The amount of light more typical in everyday experience, though much larger than the smallest amount perceivable by the human eye, as the energy of 1 mole of photons. Its energy can be computed by multiplying the photon energy by the Avogadro constant n sub a equals 6.022140076 times 10 to the 23rd inverse moles, with the result of 216 kilojoules about the food energy in 3 apples. Determination. In principle, the Planck constant can be determined by examining the spectrum of a blackbody radiator with the kinetic energy of photoelectrons, and this is how its value was first calculated in the early 20th century. In practice, these are no longer the most accurate methods. Since the value of the Planck constant is now fixed, it is no longer determined or calculated in laboratories. Some of the practices below to determine the value of the Planck constant are now used to determine the mass of the kilogram. The below given methods accept the below given method. Okay, no, that's kind of awkward. I'm just going to say the methods below. The methods given below. All of the methods given below. All of the okay. Rewording sentence for clarity. All the methods given below except the X-ray crystal density rely on the theoretical basis of the Josephson effect and the quantum Hall effect. Josephson constant. Main article, magnetic flux constant. Magnetic flux quantum. The Josephson constant, K sub j, relates the potential difference U generated by the Josephson effect at a Josephson junction with the frequency V of the microwave radiation. A theoretical treatment of Josephson effect suggests very strongly that K sub j equals 2e divided by h. K sub j equals V divided by U equals 2e divided by h. The Josephson constant may be measured by comparing the potential difference generated by an array of Josephson junctions with the potential difference which is known in SI volts. The measurement of the potential difference in SI units is done by allowing an electrostatic force to cancel out a measurable gravitational force in the Kibble balance. Assuming the validity of the theoretical treatment of the Josephson effect, K sub j is related to the Planck constant by h equals 8 lambda, h equals 8 alpha divided by mu sub 0, c sub 0, k sub j squared. Kibble balance. Main article, Kibble balance. A Kibble balance, formerly known as a watt balance, is an instrument for comparing two powers, one of which is measured in SI watts and the other which is measured in conventional electrical units. From the definition of the conventional watt, W sub 90, this gives a measure of the product K sub j squared R sub k in SI units, where R sub k is the von Klitzing constant, which appears in the quantum Hall effect. If the theoretical treatments of the Josephson constant and the quantum Hall effect are valid, and in particular assuming that R sub k equals h divided by e squared, the measurement of K sub j squared R sub k is a direct determination of the Planck constant, h equals 4 divided by K sub j squared times Rk. Magnetic resonance. Main article, gyromagnetic ratio. The gyromagnetic ratio, gamma, is a constant proportionality between the frequency V of nuclear magnetic resonance. Okay, I gotta just pause here. Alright, let's finish this. Magnetic resonance, gyromagnetic ratio. The gyromagnetic ratio gamma is the constant of proportionality between the frequency v of nuclear magnetic resonance or electron paramagnetic resonance for electrons in the applied magnetic field v equals gamma b. If it is difficult to measure gyromagnetic ratios precisely because of the difficulties in precisely measuring b, but the value for protons and more at 25 degrees Celsius is known to better than 1 part in a million. Now that's a little confusing. To 1 part and to 1 to uncertainty of 10. Whoa, what did I just do? To uncertainty of math 10 of 10. What day? 10 to the minus 6. Where protons are said to be shielded from the applied magnetic field by the electrons in the water molecule, the same effect that gives rise to chemical shift in NMR spectroscopy. Reworded. Uncertainty. Oh, I'm getting bit by bugs. Heck. Ooh. The protons are said to be shielded from the applied magnetic field by the electrons in the water molecule, the same effect that gives rise to chemical shift in NMR spectroscopy. And this is indicated by a prime on the symbol for the gyromagnetic ratio, gamma prime. The gyromagnetic ratio is related to the shielded proton magnetic moment, mu sub p, the spin number I equals to half for protons to reduce Planck constant. Gamma prime of p equals mu prime of p divided by I h bar equals 2 mu prime over h bar. The ratio of the shielded proton magnetic moment mu sub p to the electromagnetic moment mu sub e can be measured separately into high precision as the imprecisely known value of the applied magnetic field cancels itself out in taking the ratio. The value of mu sub e in Bohr magnetons is also known. Wait, shouldn't that be magnetrons? Bohr the Bohr magneton. Alright, well, I guess that's not air. It is half the electron G factor. Okay, but they don't even talk about this, so I'm going to link to this. Bohr magnetons link. Hence, mu prime equals mu prime over mu e times g sub e times mu b divided by 2 mu gamma prime equals mu prime divided by mu sub e times g sub e times mu sub e b divided by h bar. Further complication is that the measurement of mu sub p involves the measurement of an electric current. This is invariably measured in conventional amperes rather than in SI amperes, so a conversion factor is required. The symbol is used for measuring gyromagnetic ratio using conventional electrical units. In addition, there are two methods of measuring the value, a low field method and a high field method, and the conversion factors are different in the two cases. Only the high field value is of interest in determining the Planck constant. Okay, a bunch of this math, I don't want to read it all. Substitution gives the expression for the Planck constant in terms of this and all that. Faraday constant. The Faraday constant F is the charge of 1 mole of electrons equal to the Avogadro constant N sub A multiplied by the elementary charge E. It can be determined by careful electrolysis experiments measuring the amount of silver dissolved from an electrode in a given time for a given electric current. Substituting the definitions of N sub A and E gives the relation to the Planck constant, where F is the Faraday constant. X-ray crystal density. The X-ray crystal density method is primarily a method for determining the Avogadro constant N sub A. The Avogadro constant is related to the Planck constant, but as the Avogadro constant is related to the Planck constant, it also determines the value for H. The principle behind the method is to determine n sub a as the ratio between the volume of the unit cell of a crystal measured by, let me hyperlink this, alt sub v, crystal a published changes, hyperlink to crystal added, where did it go? The principle behind the method is to determine n sub a as the ratio between the volume of the unit cell of a crystal measured by X-ray crystallography and the molar volume of the substance. Crystals of silicon are used as they are available in high quality and purity by the technology developed for the semiconductor industry. The unit cell volume is calculated from the spacing between two crystal planes referred to as D220. The molar volume V sub m SI requires the knowledge of the density of the crystal and the atomic weight of the silicon used. The Planck constant is given by all that. Particle accelerator. The experimental measurement of the Planck constant and the Large Hadron Collider was carried out in 2011. A study called PCC used a giant particle accelerator. The study called PCC using a giant particle accelerator helped to better understand the relationships between the Planck constant and measuring distances in space. Okay, that's kind of confusing. I don't really know what they're talking about here. So let me see if I can find a citation. Let me go Large Hadron Collider, Planck Constant. And then let me Google PCL. PCC. It looks like they don't have a source for that. Note, the quantum of action, a historical name for the Planck constant, should not be confused with the quantum of angular momentum equal to the reduced Planck constant. Sometimes in literature, people refer to h bar as the Dirac constant, named after Paul Dirac. Okay, we're almost done. I'm just going to go to the top and read these values. Constant H, SI unit 6.62607015 times 10 to the minus 34 joule Hertz. Units with electron volts 4.135667 times 10 to the minus 15th electron volts Hertz. Planck units 2 pi E sub p TP. Wait, what? 2 pi Planck energy times Planck time. H bar equals 1.054571 times 10 to the minus 34 joule seconds. Units with electron volts 6.582. 6.582 times 10 to the minus 16th electron volts times seconds. Planck units equals 1 Planck energy times 1 Planck time. HC 1.98644586 times 10 to the minus 25th joule meters. Units with electron volts 1.239841198 electron volts times micrometers equals 2 pi Planck energy times the Planck length. Constant H bar times C equals 3.16152677 times 10 to the minus 26 joules meters. Units with electron volts equals 0.197326980 electron volts micrometers. And the Planck units Planck time, Planck energy times Planck length. And let's look at this. Okay, I think we already looked at that. Well, classical theory says as it approached 5,000, it would become infinite amount of wavelengths. A schematization of the Bohr model of the hydrogen atom. The transition shown from the n equals 3 level to the n equals 2 level gives rise to the gives rise to visible light of wavelength 650. Gives rise to visible light of wavelength 656 nanometers red, as the model predicts. N equals 2 to n equals 3. Okay, look at that one. I think we're just cycling. And references. Okay. And I'm going to end the video.